Okay, so let's quickly look at an example of a geopotential height. This map is showing January of 2003 geopotential height of 500 millibar surface. 500 millibar is the pressure. How does its height vary over the globe? Looking from the northern pole for that month. So that's obviously boreal winter month. And the unit here is decameters, which means you go from 588 decameters plus 6 decameters. That's the interval between these contours. 6 decameter is 60 meter. For whatever reason, that's the unit. But the outer edge here is in the tropics, so you can see Philippines here, northern tip of South America, Atlantic Ocean here, West Africa, and so on. India is over here, the southern tip. So what are we looking for? We are going from about geopotential height of the 500 millibar being 5.88 kilometers. 5.88 kilometers, that's about the middle of the atmosphere. 500 millibar tends to be about the middle of the atmosphere. Okay, towards the poles where the height is dropping to about 4.98 kilometers. So almost a how much 1 kilometer drop, right? So the height of the 500 millibar is higher in the tropics, as you can expect, because the air column is warmer and pressure drops off more slowly in the tropics than the higher latitudes where the colder temperatures and pressure surfaces are closer to the surface. In some sense, you're squeezing the atmosphere, denser atmosphere, into a smaller volume, right? We will see that in a minute. So whether people can look at geopotential heights and say a lot of things. There's a relation between circulation, geopotential height, and it means something when the geopotential goes higher than average or lower than average, and so on and so forth. So that's the dynamic reason why they prefer the geopotential as a convenient property or quantity to deal with. So here a meridional section is again being shown for annual mean conditions. What is shown here is actually deviation from the average geopotential height at each depth. So here pressure coordinate is used as we are dealing with geopotential heights, and this goes from the southern pole to the northern pole. So at any given height, so at 800 millibar, average geopotential height is subtracted. So what you are seeing is whether at that level the tropics are higher than the average of all longitudes or of all global mean, or lower. So as you go to higher latitudes, they are negative numbers, which means they are below the global average, and when you come into lower latitudes, they are above the global average. So it's domed up in the low latitudes and domed down in at higher latitudes, which is essentially what this is saying. So if you take an average and subtract, you will get negative numbers here and positive numbers here, right? That's what this is saying. Okay, so this says a lot about pressure gradients. Where is the rising motion? Where is the circulation interpretable in terms of the geopotential height differences, and so on and so forth. Okay, slowly we'll get used to this, but in the meantime, let's look at the pressure, surface height, and mean temperature. So we had written Z as a function of pressure equal to R times integral P to PS, T over G, dP or P, right? So if you just discretize this and look for delta Z, a small Z2 minus Z1 of a particular pressure surface is going to be P2 to P1. So you're not going all the way from the surface to that height, but you're just looking for a thickness of a particular pressure layer. Okay, that's going to be T over G, dP over P, because you are remaining within a small band. You can use average temperature and integrate from P2 to P1. Okay, remember this is reversed to remove the negative sign. What do we get out of that? Basically, this helps us with this. If you look at Z2 and Z1, so we are trying to look at the average thickness of this pressure range from P1 to P2. Okay, you can think of this as a stratified layer, for example. What this is saying is, as you go up in height, the slope of the pressure surface is going to continuously increase from the pole towards low latitudes, or is continuously decreasing negative slope here, going from being very high in the tropics to decreasing towards the poles, but the slope is higher at higher altitude. Okay, what is shown here as these dots is the arrowhead, so that's the wind coming towards you. Why are we doing that? We will see that the pressure gradient is obviously important, right? So we are talking about increasing pressure gradient with height. So remember, in each of the surface the pressure is constant, but the slope of Z1, the geopotential height, corresponds to how the pressure gradient is changing from there to there, right? You can draw a Z and look at pressure gradient along a Z, for example. Okay, so what is it good for? We will see that pressure gradient can be balanced by the rotational effect, and we'll get something called geostrophy. It also means that this increasing slope gives us a certain increase in that wind. So that's what this is showing. The winds are weaker here and they are much stronger here. Okay, we are jumping a little bit ahead, but we'll come back and remind ourselves of this figure. Turns out to be very critical. Remember that the tropopause gap we saw in the temperature distribution with height and latitude, and we said there is a gap in the subtropics. Basically that corresponds to these kind of jets that create lots of interesting dynamics as well. I think you know where that goes. You heard of jet streams, right? So we will eventually come back and see how these vertical variations in winds are created. What are the vertical variations in winds called? Basically they are called shear, right? The change in the direction or magnitude of the wind is going to give you a gradient of winds we call shear. If it's in the vertical, obviously it's vertical shear, but you can also have horizontal variations and get horizontal shear. But typically these correspond to energy stored in the system. So potential energy. Why do we want it? Basically you can always convert those to kinetic energy, right? So they can lead to mixing and other things happening both in the atmosphere and in the ocean. So lots of interesting things to learn, but just remember the concept of geopotential height, which is just the pressure coordinate telling us height of a particular pressure surface. Pressure surface varies with latitude and longitude, so geopotential height, or the height of that pressure surface, varies with latitude and longitude.